Hey everyone, we're back. It's another exciting day. Today we're going to talk about a whole new idea, and that is improper integrals. This is another kind of integration that we've kind of not thought about up to this point. And I'm just going to introduce it with a simple example. So here we go. What we want to do is find the area under the curve, y equals x squared, between x equals 1, so there's x equals 1, let's say, and some arbitrary value somewhere along the axis, let's call it R. So that's a terrible R. So we're going to find this area. Of course, we know how to do that because it's just an integral. So we've done this kind of thing many times before. Let's give it a name. Let's call it A. And we can just do that integral, right? The integral of that is minus 1 over x. And we're going to evaluate that between 1 and R. And so that's going to be, well, it's going to be minus 1 over R subtract minus 1 over 1. And so when we simplify that, we're going to get 1 minus 1 over R. So there's the area up to the point R. So let's call it A sub R. So the area under the curve between x equals 1 and x equals R is given by this thing. So for example, if R is equal to 2, the integral between 1 and 2 here, that's going to give A sub 2 is 1 minus 1 over 2, which is a half, right? And if I say, what's the integral up to 3? That's going to be 1 minus 1 over 3, so that's going to be 2/3. And we could keep going. In other words, we could make this longer and longer. We could take this R and slide it off to the right. We can make R bigger and bigger and bigger. And in fact, we could take it, as the Eagles say, to the limit. And sorry, that's the only joke you're going to get out of me. You can take it to the limit as we take this whole thing off to the right. And so we effectively get what I'm going to call, let's call it A sub infinity. I'm going to write it that way, right? It's the limit, in fact, as big R goes to infinity of that integral. The limit as R goes to infinity for that thing we just did. And we can evaluate that limit. This is a pretty simple limit compared to what we've looked at recently. So this is just 1 minus 1 over R, right? And this turns out to be, well, 1. So isn't that pretty amazing? This is actually an infinitely big region. Think about the region I'm enclosing here. This region is infinitely long. It goes on forever under this curve. It just keeps going. It gets smaller and smaller and smaller. It gets closer and closer to the x-axis as I travel along this curve. So the region is infinitely big. Infinitely big. It's really stretched out. But it has a finite amount of area under it. The amount of area under there is exactly 1. And this is what we're going to call an improper integral. I'm going to denote this thing here that I drew with the limit, I'm going to call that an improper integral, and I'm going to write it as the integral from 1 to infinity. Right? Infinity is not a number. I can't plug infinity in. This has no meaning in terms of Riemann sums and all of that kind of thing, because we can't plug infinity in. We have to build a bunch of intervals. We have to build those dx's. We've got that whole argument to make. It makes no sense if you go back to what an integral means, a definite integral, and think about how I divide that interval up between a and b. I can't do any of that if that interval along the x-axis is infinitely big. Right? The way we defined Riemann sums was literally we divided the region we wanted up into a bunch of blocks, and then we added up the blocks, and each of the blocks was a width delta x wide. Right? But if I have an infinitely long region, then I can't divide it up into n blocks of finite length. And so the whole idea breaks down. And so this makes no sense as just a number you plug in, but we can make sense of it by thinking of it as the limit that endpoint, the R in this case, gets slid off to the right infinitely far. So that's basically the idea of improper integrals. Let's write down the definition. And so here's the definition, straight from our textbook. This is precisely what I just defined, right? This definition here is what I mean by an improper integral between a and infinity. In our case, a was 1. So a is a fixed number, and then we look starting at a all the way out to infinity. And we just add up those areas in the limit. We say it converges. That integral converges if it actually adds up to a finite number, like our example did. Our example, let's go back, the value, in other words, in this case, the total area was a finite number. It was 1. So it didn't go off to infinity. It didn't get bigger and bigger and bigger. It's actually a finite value. And so that is what we're going to call converging. So that integral converges. And think about what it means. It means the total area here is 1. So it has the area that you'd expect. You know, here's 1 on the x-axis. So, yeah. And there's 1 on the y-axis. This box I just drew here, let's make it blue, this box that I'm colouring in blue has area 1 because it's 1 wide and 1 high. Well, what we've just shown is that the area under this curve off to infinity has exactly the same area as that box. Right? This is a finite box of 1 by 1. My scale's a bit wonky. This is a 1 by 1 square. Well, that has exactly the same area as all of the region under that curve, which is kind of freaky, right? Because I can draw this area, but this is an infinitely big region. All right, well, maybe you're not excited by that. I am. And you're not here, so I'm very excited. All right, so it diverges if that thing goes off to infinity. In other words, if this limit doesn't exist, if the limit gets infinitely big or becomes really, really negative and goes to negative infinity. And we can define these definite integrals in the same sort of way, starting at a and heading to the left. If you think about what that second one, the left's right. If you think about what that second one means, we're thinking about some axes and you've got some function, you know, here's your function f of x, y equals f of x. And we're asking for the area under the curve from minus infinity. So, you know, going all the way back in that direction. So all the way back to minus infinity from some point A. So we're thinking about area under a curve in the infinite region going off to the left here. So this one heads off to the left, this one heads off to the right. Let's do another example. All right, so a very similar kind of example. In this case, we want to find the area under the curve from 2 to infinity. So we can do this, and we know how to do it because we've got the definition right above us. So let's take the limit as x goes to infinity of the integral from 2 to r. We always need to do this. If you just plug in infinity, unfortunately, I'm going to mark it wrong. Sorry about that, but we need to take this limit. This limit's important. So we're going to take the limit as x goes off to infinity, but then we're going to do the actual integral, and the integral of 1 over x is just the natural log of x. Isn't it nice that we've got integrals that are easy to do for a change? So limit from 2 to infinity. So we're going to take this limit, and, ooh, I did a terrible boo-boo here, right? I'm so used to drawing an x. This is not an x, this is an r. So we're taking the limit as r goes to infinity. The limit as r goes to infinity, there we go, or in this case that one. The limit as r goes to infinity, man, I did all of this wrong. That should be an r2. What am I doing? The limit as r goes to infinity of the natural log of the absolute value of r minus the natural log of the absolute value of 2. That's just some number. And then we've got to take this limit. So the limit as r goes to infinity of log r. Well, here's a graph of log. It looks like that. Well, it's a terrible graph of log, but let me draw it again. The graph of log looks something like this. Remember, it crosses the x-axis at 1. There's the rest of the y-axis. Here's a graph of the natural log of, well, let's call it r. So this is a graph of the natural log of r, and there's the r-axis. What happens as r goes to infinity? As r gets big, log gets big. Log just keeps getting bigger and bigger and bigger. That limit is infinite. This is a perfectly well-defined number. It's log 2, it's just some number. But this piece of it is going off to infinity. So this integral that we just calculated, it diverges, right? This word, it goes off to infinity. The limit does not exist, in other words. So the integral diverges. Okay, so that's a nice mathematical name. Think about it, what it means geometrically. It means the area under this curve from 2 off to infinity is going to infinity. In other words, there's an infinite amount of area under that curve. Think about what the graph of the previous one we looked at was the graph of 1 over x squared. So 1 over x squared would pass through, well, when x is 2, this would be a quarter, right? So when x is 2, it would be a quarter. 1 over x squared is always smaller than 1 over x. It's going to look something like that. And we found that the area under this curve was 1. And that means, you know, it's smaller than 1. It's the graph of 1 over x squared is always below the graph of 1 over x. And so the graph of 1 over x is going to have more area under it. And in fact, in this case, it's going to have infinite area, whereas the area under this one is going to be finite. And notice I could have integrated from 1 or 2 or 5 or 100 or 12. This number played no part. Whatever I plug in there, I'm going to get a positive number, right? Not a positive, but I'm going to get a real number. So I'm going to take the log of 1 or the log of 12 or the log of 100. It doesn't matter. This is always going to be some real number, but it's not going to change the fact that this is going off to infinity. So the area under the curve 1 over x is going to be infinite. And in fact, if I scribbled out the 1 here, 2 there and put a 1, it would still diverge. So we've seen two of these examples, convergent and divergent improper integrals. Let's look at some more examples. So let's build on this. I'm sorry, my terrible handwriting today. I don't know what's up with me. But we just saw two examples. Firstly, we had the integral of 1 over x squared between 1 and infinity. And secondly, we had the integral of 1 over x from 1 to infinity. Well, we did 2, but 1 works as well. We saw that the second one diverged, the first one converged. What happens to all the other cases? So we can just think about the power functions. X to the power of p, right? P is 2, it converges. P is 1, because this is a 1, remember? It diverges. What happens for all the other cases? Well, we can calculate that. So we just simply integrate 1 over x to the p between 1 and infinity. And this is what we get. And we know what x to the p is. We know what 1 over x to the p is. We can write it as x to the minus p. And that's a fairly straightforward integral. We know how to do this. And we're going to work onto the assumption here that p is not equal to 1. Because if p is equal to 1, then we've got the special case we've already looked at, because the integral gives us a log. But if it's not equal to 1, then we know that the integral is just a power rule. So we add 1 to the power and we divide by that power. So that's minus p plus 1. And then we've got the limit. And we evaluate it between 1 and r. So just plugging all of that in gives us what we're looking for. So we get this nice limit, right? And that second term, this is just a 1 on the top. There's a common factor here. I'm just going to pull it out. It's 1 minus p. And then we're left with the limit. Remember, we can pull constants out from limits. So I'm just going to factor that 1 over p minus 1 out from both terms and write it out the front. And what we're left with is the first term is going to be 1 over r to the power of 1 minus, well, hang on, I've got to change the sign, because r to the power of minus p plus 1 is the same as r to the power of minus p minus 1, and that's the same as 1 over r to the p minus 1. So this is 1 over r to the p minus 1, and then I'm going to subtract, well, there's just a 1 there, because I took all the other factors out the front. All right, so there's our limit we've got to evaluate. So here's what we're trying to evaluate. Let's imagine for a moment that p is bigger than 1. Suppose that p is bigger than 1. Remember, we cut off the case here. We're not looking at p equals 1. So let's look either side. Suppose p is bigger than 1. So then I'm looking at this, and the important thing that I need is the value of p minus 1. So if p is bigger than 1, then p minus 1 is bigger than 0. Okay? So we're looking at a number in the denominator where p minus 1 is bigger than 0. So it's positive, right? The power there is positive. The p minus 1 is positive. So that truly is in the denominator. You know, p minus 1 might be a half, or p minus 1 might be 5, or p minus 1 might be 0.1. But either way, any of those ways, this is r to a positive power. And so that term, in this case, r to the positive power, that thing is going to go to infinity as what happens? As r goes to infinity. So what's going to happen to 1 over it? So 1 over that number is going to go to 0. And that's what we wanted to calculate, right? You might need to play with a few numbers to convince yourself that's true. Think about it the other way around. What happens if p is less than 1? Well, now we know that p minus 1 is less than 0, right? Because if p is less than 1, I'm subtracting the 1 on the other side. P minus 1 is less than 0. Think about what that means. This is r to the power of p minus 1. But p minus 1 is negative. So this is really in the denominator. This is r to the power of some positive number. Think about, imagine p was 0. There's a good case. Then this is r to the minus 1. So that r here is really in the denominator. So that thing must go to 0 as r goes to infinity, which means 1 over it goes to infinity. right? And that's what we're interested in. 1 over this thing must go to infinity. Because when p minus 1, when this thing here, when that value is negative, then what I'm really looking at is 1 over something. And so as that something gets big, the whole quantity must go to 0. But what we're actually interested in is the reciprocal of what I was thinking about there. All right, summary. Don't want that. Let's make a summary of this. In the case where this quantity goes to 0, in other words, where this quantity goes to 0, what I'm doing is getting 1 over 1 minus p multiplied by minus 1, because that's gone to 0. So what we're left with is 1 over p minus 1. Because, let's do it off to the side, what I'm getting in that case is if p is bigger than 1, so just looking at this, when p is bigger than 1, that integral, let's put it here, that integral is equal to that, and I get a 0 when I take the limit, and then I'm subtracting 1, and when I multiply that out, that's minus 1 over 1 minus p, or flipping the signs, both of them, I get 1 over p minus 1. So that's what happens when p is bigger than 1. What happens when it's not bigger than 1? Well, the integral diverges. Right? It diverges when it's less than 1. It diverges because this quantity is going off to infinity, which means this quantity is going off to infinity. Taking 1 from it doesn't change anything. It's going to infinity. And so this is diverging. And it also, we saw that it diverged when p was equal to 1. So it turns out that p equals 1 is the dividing line. If the p value is bigger than 1, then the integral, this p integral I'm going to call it, that integral converges. You get a finite number, here's the finite number. If p is less than or equal to 1, it diverges. I will note that the book did it with an a here, and so they give this, it's not a very straight line, was it? They give this related formula that has an a in it, but it's not very important. If you need that formula, you can find it in the book. But the important part is, either way, whether there's an a there or not, it converges when p is bigger than 1, and it diverges when p is less than or equal to 1. Less than or equal to 1. So there really is a dividing line there between the integral of 1 over x and then slightly bigger. So we know from this, for example, we can immediately say that the integral, let's do it in a different color so that we can read, the integral, let's say from 1 to infinity, what's happening? The integral from 1 to infinity of 1 over x to the power of 1.0001 dx, that converges, right? And it converges, and in fact it's going to be equal to 1 over p minus 1, which in this case is 1.000, how many o's did I have? 1 minus 1. So that integral is going to be equal to 1 over 0.0001. There we go. There's the integral. So I'm just using the p-value. The p-value here is 1.0001. Did I put the right number of o's in there? So we can work this out now because we have a value to actually calculate it. But more important than actually calculating it is knowing that test. So you need to know this test in the purple box. You need to know that the the p integral diverges when p is less than or equal to 1, and it converges when p is bigger than 1. Let me give you an example, p being less than 1. For example, p is equal to minus 3. Are we surprised that diverges? Think about what it is. It's x to the power of minus 3 integrated between 1 and infinity. Right? We're talking about that integral. Well, that's the same as the integral between 1 and infinity of x cubed. Right? This is why the negative, once they get negative, of course they diverge. What does that look like? It looks like this. Here's the graph. Right? We're starting at 1 here, and then we're adding up all the area. So we're adding up all of that area off to infinity, and we're saying, yeah, that diverges. Right? That is not a finite area. It can't be a finite area. This area just gets bigger and bigger and bigger as I head off to the right. So of course this thing diverges. Right? It's less obvious maybe between 0 and 1 when you've still got the x is really in the denominator. But it's once it's negative, then of course it must diverge. All right, so now I'm just trying to give you some intuition on what these things mean. Let's look at a couple of examples. All right, so here's a different kind of question, and I've got the theorem from the book here, by the way. This is their p integral theorem. But here's that's an interesting question. We're not going to be able to integrate this. I don't know how to integrate this. It either converges or diverges. If it converges, that means there's a finite answer, right? There's a number that comes out to be. And if it diverges, you're just going to get infinity coming out. There's an infinite number of area under the curve. I don't know what the answer is in terms of the actual integral. I don't know how to do it. But we can work out whether it converges or it diverges, because think about cosine for a minute. If you think about cosine, you know that cosine, and you might remember this from Calc 1, but you know that cosine is always between -1 and 1, right? The range is -1 to 1. The cosine function just oscillates between -1 and 1. And so when I square it, it's going to oscillate between 0 and 1. So the biggest it can get is 1, and the smallest it can get is 0, because I'm squaring it, so the negatives become positives. All right, the cosine function it looks something like this when you square it. That's not a very good picture, but the cosine squared looks something like this. So it oscillates between 0 and 1. This must be what? Pi over 2. This is 3 pi over 2, and so on. So if it oscillates between 0 and 1, I actually can say something about 1 plus x squared. I know that it's positive, so I can multiply or divide by it without changing the inequalities. This thing is always greater than or equal to 0. In fact, it's always greater than or equal to 1. But the fact that it's always positive means I can divide by it. So I can take that inequality and divide it by 1 plus x squared. So on the right, I get 1 over 1 plus x squared. And on the left, I get 0 over 1 plus x squared, right? Just divide the whole thing by 1 plus x squared. Of course, that's stupid, so let's just get rid of that and call it 0. But I know something about the cosine. But look at this. I now know that the cosine, this is the function I'm interested in, right? The reason I did that fun little calculation, and I know you loved it, the reason I did it is because that's the thing I want to integrate. And I know now that it's always smaller than this, right? Whatever the value is for that purple function, it's always less than or equal to that value. But let's think about this denominator here. Think about 1 plus x squared for a minute. 1 plus x squared. Well, that always has to be bigger than or equal to x squared, right? It's actually always bigger than x squared. It's always 1 more than x squared. So if it's in the denominator, that means that this must be less than 1 over x squared. Does that make sense? I can rearrange this. Rearranging this inequality here, I'm going to take the x squared and divide it over there, and take the 1 plus x squared and divide it over there. If I play that game, then I end up with 1 over x squared on this side is greater than or equal to 1 over 1 plus x squared. Just doing the algebra, you might see that this is true now. Right? Just rearranging this expression. I think you agree that this is true. So I'm just rearranging it to come up with this. And when I write it backwards, I get that. Another way to think about it is, look at the denominator here. The denominator here is always bigger than the denominator there, which means 1 over that denominator must be smaller than 1 over this, because this has got a bigger number in the bottom. So it must be 1 over, it must be smaller, if that makes sense. All right. But the important thing that we've just said is that the cosine squared of x divided by 1 plus x squared, that thing we wanted, it's always greater than or equal to 0. And if I read along these inequalities, I find that all of that is less than or equal to 1 over x squared. But hang on, I know about the area under that curve. I know the area under this curve, between 1 and infinity, is finite. And this function is smaller. Right? Let me show you a couple of graphs to try and make this sink in. So there's our inequality, and here's a graph from Desmos. This blue curve, that's y equals 1 over x squared. That's really hard to read, right? That's y equals 1 over x squared. The red curve down here, that's the one we're interested in. That's the graph of cosine squared of x over 1 plus x squared. And you can see it's alternating, or it's oscillating, I should say, but it's always smaller. The y value is always smaller. The red curve is always smaller than the blue curve. The y value of the red curve is always smaller than the y value of the blue curve. That's exactly what this says, right? If I zoom out a bit more, in a kind of weird way, I've zoomed out because I've made the x-axis bigger. This is now going up to x equals 20, but I've made the y-axis only go up to 0.5. You can see that this oscillation continues, right? It continues, and the red curve stays under the blue curve. That's what my little calculation here is doing. And the reason that's important is because now think about the question we were asked. We were asked to do the integral. We were asked to evaluate this integral down here. And that integral down there is the area between 1 and infinity, and 1 is about there, right? So the area under the curve between 1 and infinity, I'm talking about this red area, right? So we've got to add up this red area. And it's the area between x equals 1, which is right here, and going off to infinity. We've got to find whether that converges or diverges, whether that area is finite or not. Well, we know the area under the blue curve is finite. The area under the blue curve from 1 to infinity. So all of this, when I add all of this blue region up, I know that the integral of 1 over x squared dx is equal to 1. I could do that integral, right? We actually did that integral. Let's make it black so we can see it. We did that integral. It's 1. It's finite. It converges. In other words, the total area under the blue curve, starting at 1 and going off to infinity, is 1. It's finite. It converges. And therefore, the area under the red curve, which is less, must also converge. And what I've just described is what's known as the comparison theorem. Let me write it down. So here's a summary of what I just argued. The area under this complicated function is going to be less than the area under the blue function. And I conclude that because I know that the y value of that complicated function is always less than or equal to 1 over x squared. And I know that the integral of 1 over x squared converges. That improper integral converges. And so I conclude that this is actually going to be a smaller number because it's just the area. It's the area that I've shaded in red here. And it's going to be smaller than the area under the blue curve because that's all of the red area plus this blue area. And I know that's a finite number. So the red area is smaller, it must be a finite number too. And that's all we're saying. And that argument is called the comparison theorem for these improper integrals. And let me show you the theorem from the book. And here it is. It's worded exactly like, well, they've written the inequality the other way around. But if you know that your function g is smaller than f, and you know that the improper integral of f converges, so in our case this is 1 over x squared, and the g is the cosine one, cosine squared x over x squared plus 1. So if I know that g is always less than f, and they're positive, so it's a positive area, and I know that the integral of f, the improper integral of f converges, then the improper integral of g on the same region will also converge. But vice versa, if I had something that, if I knew that the function g itself, the smaller one, if I knew that the smaller one diverged, then the bigger one must diverge, right? If f is, if the area under g is infinite, and f is always bigger than g, then the area under f must also diverge. So imagine, going back to our previous example, let me draw the curve. Here's the curve y equals 1 over x squared, right? And we know that the area below that is infinite. So this is the area under that. From 1 to infinity, there's 1. So the area under, sorry, not x squared, I meant x. The area under y equals 1 over x, that is infinite. That integral diverges. The integral of 1 over x dx diverges. Well, if you give me any function that's bigger than that, here's a function that's bigger than that. It's a silly function, but here's a function that's bigger than that, y equals 1. Well, then the integral between 1 and infinity of this new function, 1 dx, that must diverge. Why must it diverge? Well, hopefully you can see it obviously has to diverge. When I add all of that area up, it has to be infinite as I go off to the right. But the idea here is that this function, which in this case I'm calling f, is bigger than this function, which I'm calling g. G is the smaller one, f is bigger than it, and there's an infinite area under the curve g, therefore there must be an infinite area under the curve f, because there's more area. So hopefully you see that these are fairly straightforward ideas. Don't get too messed up in the notation. Think about what the idea is telling you and then make sense of the notation based on that. I'm going to put a bunch of these on WebWork for you to practice, but this gives you a start on the section. Tomorrow we'll talk about the second half of this section. Thanks for tuning in. I hope you have a wonderful day.